Good evening. It is 6 p.m., but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you.
who are placed sufficiently close to each other. Yeah. And if you introduce a temperature or gravitational fluctuation, yeah, so that change in pressure will sort of make them porous. Yeah. So that sort of a problem will be more. Yeah, that will definitely go into that. Yeah. I can make it for the APS sectors. Right. But let's the first paper results in a combined comparison and just want to show personally what failure matrix is about and what is the outcome of it and where that's like. Okay. I think you will just be closer that give confidence in that you will complete. For ABS, I will confident on first and second. Third,
Mm.
last paper, that
Mm.
elementally what are including these are so fourth will have A and B. A will be the first preliminary work that I have. Okay. That maybe in the half of the month. We'll discuss it. Yeah. So that yeah. I think until that sure. Sure. Yours is 19. Wednesday. Before Monday before. 9 o'clock.
Good evening and welcome to week 3 of the live sessions for the course on computational science and engineering. This course is taught by Professor Ashok Dey, who is a member of the faculty of the Department of Aerospace Engineering at IIT Kanpur. And I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Now, over this last week, the principal uh, concepts discussed in the lectures were related to differential equations and particularly ordinary differential equations. And Professor Day looked at various forms of ordinary differential equations, the standard forms, the most standardized solution techniques. And so we'll perhaps add to that in the sense that we'll summarize some of the most important standardized forms of ordinary differential equations. And given the standard form, we'll try to identify some common techniques of solving them. Also, there was at least one question which was pending from the previous week session, which was related to the formation of orthonormal basis using some orthogonalization algorithms. So we'll be looking at that as well. And I believe at this stage, all of us might already be familiar with uh, ordinary differential equations, given that typically the behavior of most physical systems can be summarized not via algebraic equations, but rather differential equations, whether ordinary or partial. So, in the most generalized form, uh, differential equation, ordinary differential equation can be written as some coefficient a n x times the nth derivative of y with respect to x plus a n minus 1x times the n minus 1th derivative of y with respect to x and so on till you have a1x divided dx plus a0x y equals gx. And that's one of the most important cases which are of most relevance are the linear first order where you have n equals to 1. The linear second order would be n equals 2. Now, a few things to keep note of. The dependent variable y and all its derivatives such as y prime, y double prime and the nth derivative of y are of the first degree. That is, the power of each term involving y is 1 and the coefficients a0, a1, an or which are multiplied to all of these various derivatives depend at most on the independent variable x or they may be constants, but they will not be functions of y itself. And of course, there is distinction between the order and the degree of an ordinary differential equation. So typically, if you have some derivative, then this number within the brackets n corresponds to the order. So it can be, say, the second derivative or the fourth derivative and so on. Whereas if this derivative term is raised to some power, say cubed, then this refers to the degree. And here typically we'll only be dealing with linear ODEs, and that is this exponent or power will always be 1. However, the order can be as high as arbitrarily can be specified. Now, these are linear ODEs. However, a non-linear ODE is simply one that is not linear, that is, the powers can be anything other than 1. The coefficients of y, y prime, till yn contain the dependent variable y or its derivative, or if the powers of y, y prime, yn appear in the equation, then it is non-linear. So, additionally to this exponent not being 1, even if we multiply it with some function of y, this also renders the ordinary differential equation as non-linear. Also, other nonlinear functions with dependent variable or its derivatives, such as sin y or e power y prime, cannot appear in a linear equation. Now, another class of problems which Professor Day touched upon in his lectures were initial value problems, and as you can readily guess from the name itself, here when we are describing a system, we also have some additional information about the system in terms of its initial state at some predetermined timestamp, which say typically we refer to as t equal to 0. If it's a time dependent problem, or if it's in y and x, say at x equal to 0, you have some information about the state of the system. And this information can later be used to derive a unique solution for the given ODE. So in a general form, if the equation is the nth derivative of y with respect to x is some function of x, y, y prime, and so on till the n minus 1th derivative of y with information available to you as at x equal to x naught, you have some value of y, and similarly at x equal to x naught, you have some value of y prime till y power n minus 1. So if this was only a first order differential equation, say so of x, then you would have information only at some one point. If it were a second, okay, then you would have some information about y as well as about y prime, so on. And of course, such a problem is called an initial value problem. And some examples are given here, such as dy dx is f of xy, subject to y at x equal to x naught is y naught, and d2y dx2 at is a function of f of x, y, and y prime, with the information given to us. The y at state x equals to x naught is known, as well as the first derivative y prime at x equals to x naught is known to us. Another class of equations is called the separable equations, and as the name can suggest, any first order differential equation of the form dy dx equals gxhy is called to be separable or have separable variables, and it is simply arising from the fact that you have two functions, one entirely of x, one entirely of y, and we can bring them on each side such that on, say, one hand you only have functions of x, and on the other hand you only have functions of y, which you can then integrate simultaneously to arrive at the solution. And let us also solve an example of this kind to get more familiar with these type of equations. So the question given to us is dy dx equals y square minus 4. And since we are dealing with the topic of separable equations, maybe we should try to separate or bring variables of each kind to one side. So dy dx is y square minus 4, which implies that dy by y square minus 4 equals dx. And we can in fact factorize the LHS term, which is 1 by y square minus 4. So as some of you might be aware, of course, if we just expand, this becomes y plus 2 times y minus 2. And in fact, this can be factorized as some a times 1 by y plus 2 plus some b by y minus 2. And now let us try to find out what these coefficients a and b are. For that, we will just expand both sides. So equals a times y minus 2 plus b times y plus 2 by y plus 2 times y minus 2, which then becomes, if we bring like terms, for y we have a plus b minus 2a plus 2b, so plus 2 times b minus a by y plus 2 times y minus 2. Now, if we were to compare both sides of the equation, and specifically if we are comparing the coefficients of both sides, we see that the denominators are equal, and so they can be ignored. And comparing coefficients, we see that there is no y on the LHS, which suggests that the coefficient of y on the left hand side is 0. So since they are equal on the right hand side also, the coefficient of y must come to be 0. And this gives us one equality, which is a equals minus b. And on LHS, the constant is 1, whereas on the right hand side equation is 2 times b minus a. So 2 times b minus a equals 1, which implies that b minus a equals half. Now a is already equal to minus b, implies that b minus b is half, or 2b is half, or b is 1/4. If b is 1/4, then a is minus of 1/4. And so in fact, we have factorized the LHS. Let us put it back. 1 by y square minus 4 is minus 1/4 by y plus 2 plus 1/4 by y minus 2. So then our original ODE transforms as, sorry, minus 1/4 by y plus 2 dy plus 1/4 by y minus 2 dy equals dx. And if now we integrate both sides, we know that the integral of dy by y will be the natural logarithm of y, and adding a constant does not change anything. So this will be minus 1/4 ln of y plus 2. Similarly for the other term, ln 1/4 of, 1/4 ln y minus 2. And it is important to put the mod sign here just to be mathematically rigorous, as we know that the logarithm of term inside the logarithm should be positive, not negative. This equals x, and we can club all the constants from all three indefinite integrals into one. Just call it C1 for now. In fact, we can also take 1/4 on the other side. So you'll end up with minus ln y plus 2 plus ln y minus 2 equals 4x plus 4c1, which we can call some c2. And from the rules of logarithms, this will in fact become ln of y minus 2 by y plus 2 equals 4x plus c2. If we raise both sides of these equations as exponents of e, this will give us y minus 2 by y plus 2 equals e power 4x plus c2, which is e power 4x times e power c2, which is simply another constant, which we can call c3. So we end up with this. In fact, we can even simplify this further and obtain the LHS as just, or the equation as just some y equals something. And that is from the special form where we have a component of dividend type form where we have y minus 2 y plus 2. So let us try adding 1 to both sides. 2 by y plus 2 plus 1 equals c3 power 4x plus 1. And this implies y minus 2 plus y plus 2 by y plus 2 equals 1 plus c3 e power 4x. Is that 2y by y plus 2 plus 1 plus c3 power 4x. 2y is y plus 2 plus y c3 power 4x plus 2 c3 power 4x. Is that 2y is equal to y times 1 plus, I'm just rewriting the same thing again. We bring all y terms to the LHS, that is 2y minus y c3 e power 4x equals 2 times 1 plus c3 power 4x, or y times 2y minus y is y, 1 minus c3 power 4x equal to twice 1 plus c3 power 4x, which can give us y equals twice 1 plus c3 power 4x by 1 minus c3 e power 4x. And now this is other form y equals something. Okay, so we have obtained the solution for the given ODE, but have we missed out any solution? Let us just check. I will rewrite the original equation again. Dy dx is y square minus 4, or which can be again rewritten as y plus 2 into y minus 2. Now straight away we can see that plus 2 and minus 2 are the roots of the RHS. But let us see if the equality holds. If we put y equals say 2, then LHS is simply the derivative of a constant, which is 0, and RHS will also have the term 2 minus 2, so RHS is also 0. This holds. Also for y equals minus 2, LHS again derivative of a constant is 0, and RHS you have y plus 2 term, where if you put minus 2 you will end up with 0. So y equals plus minus 2 is also a solution of the given ODE. Now that we know that y equals plus minus 2 is the solution, and we have found the general solution, we should also be able to obtain those from this general form. Let us try to see if that is possible. For y equals 2, you have 2 equals twice 1 plus c3 power 4x by 1 minus C3 e power 4x, or 1 plus C3 power 4x equals 1 minus C3 power 4x. It simply means that C3 equals minus C3, which equals 0. So for C3 equal to 0, we can obtain y equal to 2. So by setting our constant term to 0, we can obtain one of the solution. But you can check and be surprised by the fact that for no choice of C3, can we have y equals minus 2. So in this case, despite knowing the solution upfront, we are not able to obtain it from our mathematical exercise. And why is that? That is because right at this very first step, when we brought the equation to this form, we should have taken care to write that this holds only for y not equal to plus minus 2. So for all y which are not exactly equal to plus and minus 2, this equation holds and can be solved as such. Whereas for these two special numbers of poles of this system, sorry, zeros of this system, no, poles of this equation, dy by y square minus 4 equals dx, we will have to work separately. And so this just gives us some perspective into how, despite rather than jumping straight away into an equation and trying to solve it from the standard algorithms available, we should also take a moment to reflect on what things can be missed and what special considerations might be lying underneath. Please allow me a second, I'll just have some water. Another system of important equations are called linear equations. And the first order differential equation of the form a1x divided dx plus a naught x times y equals gx is a differential equation. When the RHS or gx is equal to 0, it is said to be homogeneous, as we have already been talking about since the past two lectures. If the RHS, which is gx, is non-zero, then the equation is called non-homogeneous. And to bring it into the standard form of the linear equation, we simply divide the equation throughout by the coefficient of dy dx. And that gives us 1 times dy dx plus pxy equals fx. Once we have obtained the linear equation in its standard form, we have to determine px and then the integrating factor, which we define as e to the power integral of px dx. Once we have computed this integrating factor, we multiply this entire standard form of the linear equation with this integrating factor on both sides, and we see that we can then easily solve the equation. The next class of equations or ordinary differential equations are called exact equations, and there is a criterion to check for exactness. So a differential expression mxy dx, so m is a function of both x and y, plus n xy dx dy is an exact differential in a region R of the xy plane if it corresponds to the differential of some function f of xy, and the first order differential equation of the form mxy dx plus nxy dy equals 0 is said to be an exact equation if the expression on the left side is an exact differential. But how do we know if it is an exact differential? Mathematically, the criterion is laid out here. So let mxy and nxy be continuous and have continuous. First, partial derivatives in a rectangular region R defined by the ranges a less than x less than b and c less than y less than d. Then a necessary and sufficient condition that m of xy dx plus n of xy dy is an exact differential is simply the partial derivative of m with respect to y equals the partial derivative of n with respect to x, or as stated here, dou m dou y equals dou n dou x. Now, for cases where we have obtained that set of equations or the equation given to us is exact, or just to rewrite, equation mxy dx plus nxy dy is equal to 0 is exact if dou mxy dou y, which is also written as my, is equal to nx, which is in fact dou nxy dou x. Now, if the equation given to us fits this form, then this is the standard method of solution provided to us. If this holds, then there exists some function f for which dou f dou x is equal to m of xy, and we can find f by integrating m of xy with respect to x while holding y constant. This will give us f of xy as the integral of m with respect to dx plus some function of y which at this point remains unknown. And here it is simply referred to as the constant of integration because we are integrating with respect to the variable x. However, when we differentiate this equation with respect to y and assume dou f dou y is equal to nx, then dou f dou y is differential with respect to y of this integral that we previously computed plus g prime y equals n of xy, which will allow us to obtain g prime of y. And if we already have g prime of y, we can integrate it once to obtain g of y, and that will give us the original function f of xy which we are looking for. F of xy equals to constant gives us the entire family of solutions for this given exact differential equation. However, sometimes it may happen that our original criteria, which is dou m dou y equals dou n dou x, is not met, and so the given ordinary differential equation is not really an exact equation in its original form. Even then, under certain special circumstances, it may still be possible to reduce uh, the given equation to a standard form. It will not always be possible, but under certain special circumstances. And let us study what that circumstance is. If my minus nx, again my is simply dou m dou y and dou n dou x is in subscript x. So if my minus nx by n is a function of x alone, then an integrating factor for the equation becomes e power integral my minus nx by n dx. If on the other hand, if nx minus my by m is a function of y alone, then an integrating factor for this equation becomes e power integral nx minus my by m dy. And once we multiply both sides of the given equation with this integrating factor, we may be able to reduce the given equation into an exact form and then find the family of solutions corresponding to this equation. And to say illustrate this methodology, let us also solve one example which is given here. Xy dx plus 2x square plus 3y square minus 20 whole times dy is equal to 0. So upfront we can see that this is on the form some m of xy dx plus n of xy dy is equal to 0. Let us check for the criterion for exactness. The criterion, if you remember, is dou m dou y equals dou n dou x. So let us compute dou y of m. M here is simply xy. This gives us x. Let us also find dou n dou x, which is dou x of 2x square plus 3y square minus 20, which is equal to 4x. And so we see that dou m dou y is not equal to dou n dou x. And so the given equation is not exact, at least in the given form. But as we just discussed, is it possible to reduce it to an exact equation? Let's see. The criteria is given right here. We check the functions my minus nx by n and nx minus my by my minus nx by n. What was my? My is this dou m dou y, which is x minus nx is dou n dou x, which is 4x, and n is given to us as 2x square plus 3y square minus 20. Now, is the function my minus nx by n a function of x alone? Well, we do have y here in the denominator, so not a function of x alone. Let us look at the other function that we have to compute, nx minus my by n. What was nx? It was 4x, and my was simply x. M given to us is xy. Now, is nx minus my by m a function of y alone? Yes, it is. Since it is a function of y alone, we may still be able to reduce this given equation into an exact differential equation. And let us see how that can be done. To do that, we have to multiply it with the integrating factor mu of y. Mu y is equal to e power integral nx minus my by nx minus my by m dy, and we already computed this. So nx minus my by m is 3 by y dy, which is e power 3 ln mod y, and e power ln is simply y. So this is y cube. Now we multiply the equation throughout by the integrating factor, which in this case is mu of y. So okay, it's also written here. So y cube times xy dx plus y cube times 2x square plus 3y square minus 20 dy equals y cube times 0, which will be 0, which implies that xy power 4 dx plus 2x square y cube plus 3y5 minus 20y cube dy equals 0. Now let us try to compute uh, dou m dou y, which comes out to be, I mean, assuming this is again some m1 dx plus n1 dy equals 0 form. So dou m1 dou y will simply become 4xy cube and dou n1 dou x becomes 4xy cube plus 0 plus minus 0. And so we see that these two are equal, which means that the equation is now exact. Once the system has been reduced to an exact differential, we can find the family of solutions by following the methodology prescribed, which is we try to find some function f of x of y, x and y, so that fxy equals c is the family of solutions for the given equation. So let f of xy equals c be the solution. We are told that dou f dou x is equal to m, but now it will be equal to m1 since in the original form the equation was not exact. So dou f dou x equals f m1 equals x by 4. And if you try to integrate this, this will give f of xy is equal to x y power 4 dx plus some function g of y, which implies f of xy is equal to x square by 2y4 plus g of y. Note that after this integration, we are not taking an additional constants because the term g of y itself, in this case, is the constant of integration. Constant not in the real sense because it is still a variable dependent on y, but constant because here we are integrating not absolutely but only with respect to x, as this was a partial differential equation of dou f with respect to x only. So we have some form of f of xy. The second step was now to differentiate dou f with respect to y and set it equal to n. So dou f dou y equals n1, which would imply dou y of this equation is 4 times x square by 2y cube plus g prime of y equals n1. N1 is 2x square y cube plus 3y5 minus 20y cube. Is that 2x square y cube plus g prime of y is equal to 2x square y cube plus 3y5 minus 20y cube. This term gets cancelled out on both sides. Implies that g prime of y is equal to 3y power 5 minus 20y cube. And if we just integrate this one to obtain gy, this will give us y power 6 by 6 minus 20 y power 4 by 4, or g of y is equal to half y power 6 minus 5 y power 4. And if we put this equation right here, we can obtain our family of solutions. So f of xy is x square y 4 by 2 plus g of y, which we obtained as half y power 6 minus 5 y power 4. And as we saw, the family of solutions is f of xy, which equals half x square y4 plus half y6 minus 5y4 equals to some constant, say c1, because we can even get rid of this half, or x square y4 plus y power 6 minus 10 y power 4 equals c. This is the required family of solutions for the given ordinary differential equation. The next important type of ordinary differential equation is called Bernoulli's equation. And just like the linear ODE, the Bernoulli equation also has a special form, which is dy dx plus p of x times y equals f of x times y power n, where n is any real number and here n is the exponent of y. So the RHS fx is multiplied by, say, y square y cube, or something similar. This is called Bernoulli's equation. When n is equal to 0 and n equal to 1, equation 4 simply is the linear equation. And for n not equal to 0 and not equal to 1, this can be solved using the substitution u equals y power 1 minus n, which will then reduce the Bernoulli equation to a linear equation. So this substitution must be kept in mind. Again, as we were discussing about the degree and order of uh, a given ordinary differential equation, if uh, an ordinary differential equation is of order 2 or more, and if one of the solutions is given to us, then using that solution, we can reduce the order of the given differential equation and make it more amenable to solution. And the general algorithm or process is highlighted here. What basically happens is, if some solution y1 is known to us and we substitute y1 for every x in the interval, some part of the equation, which is shown here, will turn to 0. And then we have the substitution W equals U prime or W prime equals to U double prime. So that what was originally given to us as a say a second order uh, differential equation, we now substitute it and make it into a first order differential equation in order to solve it more easily. The U prime terms simply becomes W and so on. So in essence, we have reduced the uh, order of the differential equation by one. And by some careful choice of these constants C1 and C2, without any loss of generality, however, we can find another solution of the given equation, given one of the solutions, and the second solution is obtained in terms of the first as y2 equals y1x times integral of e power minus integral p dx by y1 square dx. Again, higher order differential equations were something Professor Day touched upon in this week's lectures, especially towards the later half. And for when dealing with higher order differential equations, something called the superposition principle comes into the picture. And as we have been discussing, the ordinary differential equations given to us will have an RHS. That RHS can either be zero or non-zero. If it is zero, the equation is called homogeneous. And if on the RHS we have a constant or any other function except for zero, it is called non-homogeneous. For non-homogeneous equations, we will have both uh, a general solution and a particular solution. Whereas for homogeneous equations, we'll only have the general solution. And let y1, y2 till yk be solutions of the homogeneous and nth order differential equation. Then the linear combination c1 y1 plus c2 y2 plus ck yk is also a solution of the interval. And any set y1 y2 yn of n linearly independent solutions, remember, linearly independent is a concept which we have been looking at in the context of vectors, but we'll also be looking at it in the context of differential equations, and we'll see how to check whether any given set of solutions is linearly independent or not. And if this y1, y2 till yn of n linearly independent solutions of the homogeneous linear and third differential equation is said to be a fundamental set of solutions on the interval. How to check whether they are indeed linearly independent? We arrange these functions into a Wronskian, which is something similar to a determinant but with vastly different physical meanings. And so if we arrange f1, f1 prime till f1 n minus 1th derivative of f1 as the first column, f2 and its derivatives as the second column till the n minus 1th derivative, and so on and so forth till we have the nth column as fn, fn prime, and the n minus 1 derivative of fn, and we compute this Wronskian. If this Wronskian is not equal to 0, then the set of solutions given by say f1, f2 till fn is linearly independent. If the Wronskian becomes 0, the solutions are dependent. If they are indeed linearly independent, then the general solution is composed of c1 y1 plus c2 y2 plus cn yn. And for non-homogeneous equations, there will be an additional term in addition to this general solution, which is called yp, which is the particular solution for that non-homogeneous equation. And for the case where the coefficients of a homogeneous linear equation are constant, there is a well-defined or well-laid out methodology for solving them, which most of us might already be familiar with. And if the equation is of the form ay double prime plus by prime plus cy is equal to 0, where a, b, and c are constant coefficients, then we can start by assuming a solution on the form y equals e power mx. Then y prime will simply be m e power mx, and y double prime will simply be m square e power mx. If we substitute this back into our original equation here, a times m square e power mx plus b times m e power mx plus c e power mx is equal to 0, which implies that am square plus bm plus c times e power mx is 0, which implies that either e power mx is 0 or m square plus bm plus c is 0. Now, if e power mx is equal to 0, then y is equal to 0, and this since y is 0, y prime is also 0 because it's just derivative of a constant. Y double prime is also 0, and then the equation is trivially true. So this gives us a trivial solution. However, if e power mx is not equal to 0, then am square plus bm plus c is equal to 0. And given that this is a quadratic equation, we can obtain solutions as m equals to minus b plus minus under root b square minus 4ac by twice a. Now, depending on uh, the roots, we can have different sets of solutions. And this equation, am square plus bm plus c equals 0, is indeed called the auxiliary equation of the given differential equation. This will give us two roots, m1 and m2, depending on the plus or minus sign, whichever we are taking. And there will be three forms of the general solution of 1 corresponding to the three cases. If both the roots m1 and m2 are real and distinct, when the determinant is greater than 0. If the determinant is equal to 0, then you have real and equal roots or real and repeating roots. And if the roots m1 and m2 are complex conjugate, which is the case when the determinant is less than 0. If the roots are real and distinct, then the general solution will be of the form y equals c1 e1 power m1 x plus c2 e2 e power m2 x. If the roots are real and repeated, we in fact have obtained only one exponential solution, which is y1 equals e power m1x. And then, given that we already have one solution, we can follow the discussion for reduction of solution to obtain the other in the form of y2 equal y1 times e power integral px dx by e power. Yeah. If we have the one solution y1, we can have the other solution as y equals y2 equals y1 times e power minus integral px dx by y1 square dx, which is also shown here. And the general solution then becomes y equals c1 e power m1x plus c2 x times e power m1x. In fact, if we had three solutions, the third solution would have simply become c2x square e power m1x. If there were four terms, then c4 x cube e power m1x and so on. The multiplicity of x just keeps on increasing. And if the roots are complex conjugate, then the solution is written in the form of c1 e power alpha plus I beta x plus c2 e power alpha plus I beta x alpha minus I beta x, where m1 is alpha plus I beta, the other is a complex conjugate, so alpha minus I beta. And this can further be simplified to the form y is equal to c1 e power ax cos beta x plus c2 e power ax sin beta x, or e power ax c1 cos beta x plus c2 sin beta x. And then, of course, is Gram-Schmidt orthogonalization, which requires taking successive projections. And this is something we already discussed in the last class, so we'll just solve the uh, numerical now. And okay, we have spent 1 hour looking at the concepts, so let us just break for a short while. And when we return, we'll solve the illustrative examples.
तो उसके अकॉर्डिंग वो हो जाता है ज्योमेट्री अगर समझा एक्सिस भी बनाया तो भी चलेगा उसको इम्पोर्ट कर सकते हैं यहाँ पे कैसे होगा और एक भी अभी पूछा ना उत्तर if anybody wants to apply there उसके लिए वहाँ पर उसके लिए हाँ हाँ आई guess तो anybody मतलब क्या तो यहाँ पूरे लैब अपने कर सकता है अपना नहीं 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 वो बोले ना यहाँ से किसी को करना है हाँ तो जिनका हुआ मैंने कुछ किया भी नहीं हाँ नहीं होगा ड्राइव ड्राइव पे लिए थे क्या ड्राइव पे तो नहीं था मैं लेता तो हार्ड से नहीं है क्या हाँ कल सबको दिखाना ना क्या बोले ये मेरे घर में ही हुआ लैपटॉप वो आइडिया वापस उसका कल कोई आईसी स्विच रहते ना उधर एक इशू होता मेरे लैपटॉप पर सब डेटा था ना सब वो जो स्विच होता है ना वहाँ पे वो आईसी रहता है वो इसका आई नहीं करता बहुत प्रॉब्लम नहीं बटन दबा रहता चालू नहीं होता
So let us continue with the illustrative examples for today. The first one is actually a pending exercise from the previous week. So some of you might already have solved it at home. But for the rest of you, here we were trying to construct an orthonormal basis from a given basis set, which consisted of U1, U2, and U3. And we will do this by a process called Gram-Schmidt orthogonalization. And I have already discussed the theory of this, so we'll directly jump in and use the formula available to us. Now, as we know, we leave the first basis unchanged, that is V1 is same as U1, so it's 1, 1, 1. The second basis vector V2 is equal to U2 minus the projection of U2 on V1, which is in fact U2 dot V1 by V1 dot V1 times V1, and let us solve this out. So U2 is 1, 2, 2 minus 1, 2, 2 dot V1 is simply 1, 1, 1 by 1, 1, 1 dot 1, 1, 1 times V1, which is again 1, 1, 2, 2 minus. So this is just a vector dot product. So we have 1 into 1 plus 2 into 1 plus 2 into 1 by 1 square plus 1 square plus 1 square. And this scalar is multiplied to the vector 1, 1, 1. So this is 1, 2, 2. And this is 1 plus 2, 5 by 3 times 1, 1, 1. 1 minus 5 by 3 is minus 2 by 3. 2 minus 5 by 3 or 6 by 3 minus 5 by 3 is 1 by 3. And 1 by 3. So we have V2. How about V3? Remember that V3 is equal to U3 minus the projection of U3 on V1. So U3 dot V1 V1 minus projection of U3 on V2. So U3 dot V2 by V2 dot V2 times V2. U3 is 110 110 dot V1 is 111 by V1 dot V1 times V1 minus U3 is again 110. We just found U2. It is minus 2 by 3, 1 by 3, 1 by 3 by V2 dot V2. So minus 2 by 3, 1 by 3, 1 by 3 dot minus 2 by 3, 1 by 3, 1 by 3. We have to multiply this with the vector, so I'll just bring this down for clarity. Times V2, and V2 is minus 2 by 3, 1 by 3, 1 by 3. Now let us expand this. So this becomes 110 minus 1 into 1 plus 1 into 1 plus 0 by 1 square plus 1 square plus 1 square 1 1 minus minus 2 by 3 into 1 plus 1 by 3 into 1 plus 0 by minus 2 by 3 square plus 1 by 3 square plus 1 by 3 square times minus 2 by 3 1 by 3 1 by 3 1 and 0 minus this becomes 10 plus 1 2 by 3 times 1 over 1, so this is just 2 third 2 third 2 third minus minus 2 by 3 plus 1 by 3 is minus 1 by 3 by this is 4 by 9 plus 1 by 9 5 by 9 plus 1 by 9 6 by 9 or simply 2 by 3 minus 2 by 3 1 by 3 1 by 3 and this will further simplify to minus half, so this is 110 minus 2 third 2 third 2 third plus minus half times sorry I will take the negative out, so half times minus 2 by 3 is 1 third half times 1 by 3 is 1 sixth and 1 sixth. And if we add this up, 1 minus 2 by 3 is 1 by 3 minus 1 by 3 is 0. 1 minus 2 by 3 is 1 by 3 plus 1 by 6. 2 by 6 plus 1 by 6 is 3 by 6 or half, and 0 minus 2 by 3 plus 1 by 6. So this is minus 4 by 6 plus 1 by 6 is minus 3 by 6, so minus half. And so we have obtained V1 as 111, V2 as minus 2 third 1 third 1 third, and V3 as 0 half minus half. Now note that V1, V2 and V3 do constitute an orthogonal basis for R3, but they are not orthonormal, as in individually their magnitudes are not equal to 1. You can write this as, say, some B prime equals V1, V2, V3 is an orthogonal basis for R3, but it is not an orthonormal basis. However, if we can just make each of them into unit vectors, we will obtain our orthonormal basis as well. So for an orthonormal basis, say W1 is V1 by norm of V1, 111 by 1 square plus 1 square plus 1 square. This will become root 3, so we have 1 by root 3, 1 by root 3, 1 by root 3. W2 is simply V2 by norm of V2, which is minus 2 third, 1 third, 1 third by under root of minus 2 third square plus 1 third square plus 1 third square This comes out to be 4 by 9 plus 1 by 9, 6 by 9, 2 by 3. So this becomes 6 by 9 or root 6 by 3. So minus 2 by root 6, 1 by root 6, 1 by root 6, and W3, which is simply a unit vector along V3 or V3 by norm of V3, 0, half, minus half by under root of 0 square plus half square plus minus half square. So plus half square is 1 4 plus 1 4. Root 2 by 2. So this becomes 0, 1 by root 2 minus 1 by root 2. And now we can say that E equals W1, W2, W3. Right? And orthonormal basis of R3. Now moving on to illustrative examples regarding differential equations. Let us solve this first one given to us. X divided dx plus y equals x square y square. Let us try to bring it into some form of a standard, some known standard form, so that we can solve it more easily. So dy dx plus 1 by x times y is equal to xy square. And this is in fact then similar to the standard form, which is the Bernoulli equation. Once we know that this is the form of Bernoulli's equation, we know that we must substitute u equals y power 1 minus n, and here n is equal to 2, so we must substitute y equals y power 1 minus 2 or y power minus 1, which is equal to 1 by y. So u is equal to 1 by y or y is equal to 1 by u, which implies that dy is equal to minus 1 by u square du. If we substitute this for dy, we have minus 1 by u square du dx plus 1 by u minus 1 by x equals x times 1 by u square, or du dx minus 1 by x times u equals minus x. And after the substitution, this should reduce to the linear equation, standard form of the linear equation, and let us see if that is okay. Du dx plus px u equals q of x, and indeed this has turned into the standard form of linear equation. Once this is done, we know how to solve it further. We find the integrating factor, which is nothing but e power integral px dx. Here p is minus 1 by x, and we know that the integral of 1 by x dx is ln of x. This is e power minus ln of mod x, and this simply equals x power minus 1 or 1 by x. So we multiply both sides of the equation by 1 by x. So 1 by x du dx minus 1 by x square u is equal to minus 1, which implies that is this equal ddx of u by x. V du minus u dv by v square. Okay, we'll come back to this problem. Looks like there might be something wrong. Let us go to the next one. Here we are asked to solve the initial value problem. Dy dx plus y equals f of x, and y at x equal to 0 is equal to 0. And the function of f of x is prescribed as equal to 1 if x lies between 0 and 1, both inclusive, and equal to 0 for x greater than that. So it might just help if you can have a plot for f of x. And here we are told that for 0 less than equal to x less than equal to 1, f of x is equal to 1, and it is equal to 0 for x greater than 1. So this is the value of f of x. And let us try to solve this initial value problem. Again, since the RHS, which is equal to f of x, will change depending on the interval, we can solve it in two parts. For the interval 0 less than equal to x less than equal to 1, dy dx plus y is equal to 1. And let us see if this fits any of the standard forms known to us. So we are already aware that dy dx plus p of x times y equals q of x is the standard form of the linear differential equation. So we can find the integrating factor e power integral px dx. Here p is simply 1, so e power integral 1 dx or e power x. Let us multiply both sides. of the given equation by the integrating factor, which is e power x. So e power x dy dx plus e power x y equals e power x, which implies that d dx of x times y equals e power x, or if you integrate both sides with respect to dx, where for xy equals e power x plus some constant c1, and if we divide both sides by e power x, we have y equals 1 plus c1 e power minus x. How do we determine this constant c1? We are told that y at 0 is 0, which implies that 0 is equal to 1 plus c1 e power minus 0, which implies that 0 is equal to 1 plus c1, which implies that c1 is equal to minus 1. And so for this given interval, 0 less than equal to x less than equal to 1, the solution is simply y equals 1 minus e power minus x. What about the other interval, that is for greater than 1? Now dy dx plus y equal to 0. And again, this will fit the standard form of the linear differential equation. And so we find the integrating factor, which is e power integral 1 dx in this case, or e power x. We multiply both sides of the given equation with the integrating factor to obtain e power x dy dx plus e power x y is equal to 0 times e power x, which is still 0, or d dx of e power x times y is 0, or e power x times y is some constant c2, which gives y equals c2 times e power minus x. Is it possible to obtain c2 as well? Well, we can definitely try and see if that happens. So y at 0 is 0, which implies that 0 is equal to c2 times e power minus 0, which will simply mean that c2 is 0 itself, which is not very helpful, because this will just give us a trivial solution. Can we think of some other way to obtain c2? Let us see. So till now we have obtained the solution as 1 minus e power minus x for 0 less than or equal to x less than or equal to 1, and some c2 times e power minus x for x greater than 1. Now, if our solution function y is to be continuous, that is, for continuity of y on the interval 0 to infinity, the value of y should be the same whether we approach it at 1 from the left side or from the right side. So limit at x tends to 1 from the right side should equal the limit as x tends to 1 from the left side. And so at 1, c2 e power minus 1 should equal 1 minus e power minus 1, which implies that e power minus 1 times 1 plus c2 is equal to 1, or that 1 plus c2 is equals 1 by e power minus 1, which is simply e, or c2 equals e minus 1. Therefore, the solution then becomes y equals 1 minus e power minus x when 0 less than equal to x less than equal to 1, and e minus 1 times e power minus x for x greater than 1. And this also gives me an idea that maybe I was looking in the wrong direction. This will become an exact differential, and so this LHS is indeed d dx of 1 by x times u. So first you have 1 by x du dx and then minus 1 by x square times u equals minus 1. And if we integrate both sides, what we obtain is 1 by x times u is minus x plus some constant c1, and if we take x to the other side, we have u equals minus x square plus c1x. Now, if we remember our substitution, y was equal to 1 by u. 1 by u is equal to c1x minus x square, which implies that y is equal to 1 by c1x minus x square. This is the solution to the given differential equation. Let us move to question 4, which is another initial value problem. dy dx is equal to x y square minus cosine of x sine of x by y into 1 minus x square, and we are given the initial condition that at x equal to 0, y is equal to 2. So as per usual, let us try to manipulate this equation and see if it fits any of the standard forms that are known to us. We bring y to this side, y into square dy is y square minus sin of x sine of x dx. I should imply that xy square minus cos x sine x dx plus x square minus 1y dy is 0. And this is looking familiar to the form, or similar to the form mxy dx plus nxy dy is 0. And let us check if this given equation is exact or not. So dou m dou y, where m is xy square minus cosine x sin x is equal to 2xy, and dou m dou x is equal to x square y minus y 2xy. And so we observe that dou m dou y is equal to dou m dou x, which means that this given initial value problem is the differential equation for this initial value problem is exact. So we can then proceed to find the family of solutions as we already did previously. Let some function f of xy equal to c be the solution. Now dou f dou x is equal to m, which in this case comes out to be m is already known to us, x y square minus cosine x sin x, and if we integrate this with respect to x, then f of xy will become integral of say xy square minus sin x dx plus some function g of y. This becomes x square y square by 2, and the second integral is a bit more involved, integral cosine x sin x dx plus gy. Okay, so let u equals sin x, in which case du dx shall equal cos x, or du shall equal cos x dx. So for integral, I can write this equation itself f of xy is x square y square by 2 minus integral of sin x d of sin x plus g of y. And just like the integral of x dx is x square by 2, in this case also the integral of sin x d sin x will be sin square x by 2 plus g of y. Now I differentiate or take the partial derivative of f with respect to y and set it equal to n. So dou f dou y, which in fact comes out comes to x square y minus 0 plus g prime of y is equal to n, but n in this case is exponential value, which implies that x square y plus g prime of y is equal to x square y minus y, or g prime of y is simply minus y, which implies that g of y is equal to minus y square by 2. If we substitute this value of gy back into our expression for f of xy, x square y square by 2 minus sin square x by 2 minus y square by 2. And this equal to some constant is the family of solutions. Now we are given the initial value that at x equal to 0, y is equal to 2. Let us put that in. So at x equal to 0, y is equal to 2, which will imply that 0 square and 2 square by 2 minus sin square 0 by 2 minus 2 square by 2 is equal to c. C is equal to first one goes to 0, second goes to 0, minus 2 square by 2 is minus 2, c is equal to minus 2. Therefore, the solution is x square y square by 2 minus sin square x by 2 minus y square by 2 is equal to minus 2, or just y square plus sin square x plus minus x square y square is equal to 4. This is the solution. So the given ODE. Question 5 is a word problem. Let us take a look at it. Please give me a minute. I'll just have some water. Okay. So the question says a breeder reactor converts uranium 238 into plutonium 239. After 15 years, it is determined that only 0.043% of the initial amount of plutonium has disintegrated. Find the half-life of this isotope if the rate of disintegration is proportional to the amount remaining. So we will have to make an effort to translate this word problem into some mathematical equation which we can then solve. We are told that the rate of disintegration is proportional to the amount remaining. So let us first describe the amount of plutonium remaining. Okay. So let AT be the amount of plutonium 239 remaining at any time, and we are told that the rate of disintegration is proportional to this. So dAdt is equal to some k times a, where k is the constant of proportionality, and at time t equal to 0, we had some initial amount of plutonium. Let us assume that is A0. Now, If dA dt is equal to K, let us try to solve this. So dA by A is equal to K dt. And if we integrate this, we have ln of mod A is equal to K times T plus C1. If we raise both the LHS and RHS as exponents of E, then LHS simply becomes A, RHS becomes E power KT plus C1, which is equal to some C2 times E power KT. Now, at time t equal to 0, we assume that A was equal to A naught, which will give A naught is equal to C2 e power k times 0 or C2. Therefore, A is equal to A naught times e power kt. Now we are told that after 15 years, it is determined that 0.043% of the initial amount of plutonium has disintegrated. So this is an additional piece of information. So at t equals 15 years, some amount of plutonium has disintegrated. What is the amount remaining? 0.043% has disintegrated. So some 99.957% of the original is remaining, which is in fact 0.99957 A naught. So we have 0.99957 A naught is equal to A naught times e power k into 15, which implies that 0.99957 equals e power 15k. If we take natural logarithm of both sides, ln 99957 equals 15k, which will give us k is equal to ln of 0.99957 by 15. Please give me a minute to compute this number. So this will come out to be something like 2.8673 into 10 power minus 5. And so if we put the value of k, we have a equals a naught times e power 2.8673 into 10 to the power minus 5. We are asked to find the half-life of this isotope, or the time of after which half of it has disintegrated. So the half-life implies the time after which half of the original quantity of the isotope remains. Or basically at t equals half-life th, a shall equal a naught by 2. So let us put this into our expression. We have A equals A naught e power 2.8673 into 10 to the power minus 5 given. Now A naught by 2 equals A naught times e power 2.8673 into 10 to the power minus 5 times dh over half is equal to e power 2.8673 into 10 to the power minus 5 dh. If we take a logarithm of both sides, ln point 0.5 is equal to 2.8673 into 10 to the power minus 5 dh. Dh is equal to ln point 0.5 by 2.8673 to 10 to the power minus 5. And please allow me a minute to compute this. I want to be 24174.35 years. So this is the required half-life of the isotope. So I also see that we have reached the end of our time. So thank you very much for tuning in to the live sessions for the course on computational science and engineering. I am Sourav Goswami from IIT Bombay, and I hope to see you again next week.